Next up are some algebraic approaches to dealing with some of the same ideas that we saw in the last lesson. I almost never use these purely algebraic methods, as I find the Venn diagram approach to be essentially just as fast and significantly easier to use, which to me means I have less chance of a mistake, and that's key. One of the things we need to be sure to do in passing an actuarial exam is get all the easy questions right. But for those of you who want to live life on the edge, do things the slightly harder way, here's the algebraic approach. I'm going to look at things called De Morgan's laws and the inclusion-exclusion principle. But first, I want to talk about some key words, because a lot of the hard part about questions on the fundamentals of probability is interpreting the wording correctly. So for us, when we talk about A or B, we mean the mathematical or, which means an inclusive or. It means A and or B in common English. It means a union A, union B. It means either A or B or both events occur. A and B means I just want the intersection. A intersect B, which I'll often abbreviate as AB. A or B, but not both, sort of an exclusive or, means I want to start with the union, but then I want to exclude the intersection. So if I draw a Venn diagram here, I've shaded in A union B. I want to get rid of the intersection. I want to take rid of that middle piece, and I'm left with the left crescent and a right crescent. Algebraically, what is that event? It means algebraically I want A intersect B prime, which is my left crescent, or the right crescent, which is A complement intersect B. What if you want to have neither A nor B? Well, first let's draw a picture in which I have A or B. All right, that's my diagram right here. That's my left-hand diagram. On the right-hand side, let me first just draw A prime intersect B prime. So I want to be in A prime. What's A prime? A prime is everything other than A. So I'll just punch out A. And now my blue stuff is A prime. I also want to be in B prime. So I'll punch out B, and leaving me only with stuff that's in B prime. That is exactly the inverse of my previous diagram. Right? What was blue here was A union B. That's now in white. What was white here is A union B complement. That's now blue. So what I have here is A union B complement. And this is the way that we graph neither A nor B. I'm not in A. That's why I punched out A. I'm not in B. That's why I punched out B. So there are two ways algebraically that we can write neither A nor B. I can do it as not A and not B. Or I could do it as the opposite of A and or B. What if we have three events, A union B union C? What if I want to do A prime intersect B prime intersect C prime? So first I want to be in A prime, so I punch out A, and what's left in blue is everything that's in A prime. I also want to be in B prime, so I have to punch out B, and so everything that's left must also still be in B prime. I want to punch out C as well. And so again, I have the exact opposite of what I had in the left-hand side, so now I have A union B union C complement. That's what De Morgan's laws say. Here I have the intersection of the complements is equal to the complement of the union. Right, so more generally, De Morgan's laws say that the complement of the union is equal to the intersection of the complements, and vice versa. The complement of the intersections is equal to the union of the complements. And so here's an example for you to pause and work. It's partially a wording test, partially a way of getting used to dealing with complements, and partially an application of De Morgan's laws. My auto insurance company has 10,000 policyholders. Everyone's either young or old, or male or female. So I'm going to let Y denote people who are young, and M denote people who are male. 2,000 policyholders are neither young nor male. Well, neither young nor male is young or male complement. Or I could also write it as not young, intersection, not male. Right? If you're neither young nor male, it means that you're old, female. So you're old female. And we're given that 2,000 people are in that group. There's 10,000 total policyholders. So probably being in that group is 2,000 over 10,000 or 0.2. We're told 6,000 are either young or female. So young or female. Female is male complement, M prime. At 6,000, so 6,000 over 10,000 is 0.6. At the end of the day, I want the probability of being young. I want the probability of Y. All right, so now let's just take these two pieces of information that I have. Probably Y prime intersect M prime equals 0.2. The probability of Y intersect M prime is 0.6. And put them down in the Venn diagram and see what we get. Y prime intersect M prime, so neither young nor male, means everything outside of young and outside of male, is this shaded blue region, and that we're told is probability 0.2. Probability of being young or female is 0.6. What is that in the picture? Young is everything in there. Female is everything outside of male, so that's going to add in my total complement out there. That's probably 0.6. Well, I know about 0.2. I have some missing stuff here that must add up to my 0.6. But the point here is this crescent shape, that's much easier to deal with. There's just one region instead of two. So I can say that my crescent has probability 1 minus 0.6 as a complement. What's the complement of young or female? That's going to be not young and male. Right? Because male complement is going to be male again. And that's probability 0.4. That's my shaded region here. Probability of being not young, that's chance of being not young and not male, the outside piece that had probability 0.2, plus probability of being not young but being male, which is probability 0.4. And so those add up to 0.6. The chance of being outside of this, chance of being young is 1 minus 0.6 is 0.4. Now we could have gotten that in a slightly faster way, just taking advantage of the fact if we go back up a few pictures. We know chance of young or female 0.6. Well, we know about the 0.2 outside. I just want these two shaded pieces inside. They must be 0.6 minus that 0.2 or 0.4. So I could have saved some of these steps. I just wanted to give you some more familiarity with some of the way we deal with complements. The final theory piece I want to look at is something called inclusion-exclusion, which is an attempt to generalize one of our initial axioms of probability. One of our initial axioms said the probability of A union B was the probability of A plus probability of B minus the probability of the intersection. What if we have three events, A union B union C? Well, I could do a similar thing. I could do the probability of A, so I'll shade in everything that's in A. Add in the probability of B, I'll shade in everything that's in B. Now everything that's in A and B is now counted twice. So I'm going to shade that twice as darkly as what's in either only A or only B. Now let's add on probability of C. Now the stuff that's in A and C, I'll shade extra dark because now it's counted twice in A and C. Stuff that's in B and C, I'll shade darker because it's in twice as in B and C. And in fact, the triple intersection, I'll shade the darkest yet because it's in A and B and C. It's now counted 3 times. If I subtract off the probability of A and B, I'm going to make this everything in A and B lighter. So I make the top part go from twice counted to once counted. Make the triple intersection go from 3 times counted to twice counted. Subtract off probability of AC. These two things that were twice counted now only counted once. And subtract off probability of BC. B and C only was counted twice. Now it's counted once. But now I have a problem. I have the opposite problem that I had before. Now my triple intersection is counted 0 times. The triple intersection was counted the second time, counted the third time, subtracted off once, subtracted off twice, subtracted off the third time. So it's counted 3 times, subtracted 3 times, making it counted 0 times, which is why it's now unshaded. So I need to add back in my triple intersection. All right, so that's how inclusion-exclusion works with 3 things. I do the probabilities of one, the sums of my probabilities of just one event, minus the sums of my probabilities of a double intersection, plus the probability of my triple intersection. What if I have 4 things? Well, I could do the sums of probabilities of everything once. I subtract off the probabilities of all my double intersections, and now 6 of them. I add back in all my triple intersections. But now what's happened to my quadruple intersection? It was counted 4 times in the first row. Subtract out 6 times in the second row, so negative 2 times. Added in 4 times in the third row, so now it's counted plus 2 times. So I have to subtract out 1 more time, subtract out the one counting there. And you can keep on going, more and more, right? So the probability of a bunch of unions is I do the probabilities of everything of all my singles minus the probability of all my double intersections plus the probability of triple intersections minus the probability of my quadruple intersections plus the probability of the quintuple intersections minus the probabilities of the sextuple intersections and so on and so forth. You will never run into that in the exam. It's unlikely to even run into this version on the exam. The worst that you'd really see is with a triple intersection. So let's end with a familiar example that we did before using a Venn diagram, but now I want you to pause the video and work this using the inclusion-exclusion principle. I'm going to let my notation be the same as before. I'm going to let G, B, and S denote those who watch gymnastics, baseball, and soccer. And then what's my inclusion-exclusion formula? It says the probability of the union is the probability of the single events minus the probability of the double intersections plus the probability of the triple intersections. And then I just read these out. The probability of G is 0.31. The probability of B is 0.25. The probability of S is 0.21, and so on. So I'm just copying these probabilities down from the problem. That adds up to 0.54. I want the probability somebody watches none. So I want 1 minus the probability of watching at least one. So I get 1 minus 0.454 or 0.46. All right, so that's it for the laws of probability. But before you move on to the next lessons about conditional probability, you want to be sure to work through the A1 practice problems before you move on.